Elements of computer processing. You can communicate with computers in the computer's language, which is the binary language, like telegraphy, in which a message is converted in a series of dots and dashes, such as it is necessary to have characters, words, and sentences in any spoken language for understanding conversation between humans, as well as a computer has its own elements, which are known as computer language. A combination of these digits are called bit, nibble, byte, and word. Bit. Bit is either 0 or 1. It is the smallest character which a computer recognizes. Nibble. Nibble is formed by 4 bits. Therefore, a half byte is equal to a nibble or 4 bits. Byte. 1 byte is equal to 8 bits, which is the smallest unit of storage which a computer uses to store even a single character. The character may be an alphabet, A to Z, a numeral, 0 to 9, or special characters like hyphen, asterisk, less than, greater than, question mark, plus, minus, equals to, /, hash, etc. Although computer storage capacity is measured in bytes, the processing inside the computer is done in words. Word length. A computer word is made of bytes. It can be a 1-byte word, a 2-byte word, a 4-byte word, or even more. A computer is specified as 8 bits, 16 bits, 32 bits, 64 bits, or 128 bits, depending upon the word length. Since a large word will process large quantity of data at one time, a computer using a larger word length would be a faster machine. Today's PCs are up to 64 bits. Character representation. The character keys from a keyboard are represented in binary code in the computer, that is, in the form of a set of 0 and 1. When a character is typed from keyboard, its scan code is executed from ROM, read-only memory, against the address of that key. Do you know how the address of a particular key is recognized by the ROM? The keyboard is designed in the form of a rectangular matrix. A rectangular matrix has a number of rows and columns. The intersection of rows and columns form a cell, and a cell is addressed by the row number followed by the column number. Illustration of this concept: column, row, row 1, row 2, row 3, row n. Column 2, 1, 1, 2, 1, 3, 1, n, 1. Column 3, 1, 2, 2, 2, 3, 2, n, 2. Column n, 1, n, 2, n, 3, n, n, n. A rectangular matrix. When you press A from keyboard, its address goes to ROM. Now, ROM scans the address and executes its ASCII code, American Standard Code for Information Interchange. For each character, as an ASCII code in decimal number system is defined in ROM. This ASCII code is transferred into binary form, that is, in 0 and 1, and transferred to RAM and then directed by CU to the VDU to be displayed. Binary number system. Processing inside the computer is done in the form of binary codes. Although you know what form is taken by the characters in ASCII system, yet the computation is done on binary addition system, which should be known to you. First, you should know how to convert any decimal number into the binary. An easy method of binary conversion is given below, by which only limited numbers can be changed in binary codes very easily. In this method, you can use our fingers to represent binary number 1 or 0. If a finger is open, then consider it as binary code 1. And if a finger is closed, then assume binary number 0 on that position. If you use your right hand to represent just the double number of the last one, while the thumb will represent the decimal number 1. Thus, the thumb will represent 1, the index finger 2, the middle finger 4, the ring finger 8, and the little finger will represent the number 16. Now, make the combination of fingers in such a way that adding the values of the opened fingers, the required number could be constructed. The given figure illustrates the representation of some decimal numbers: 0, 0, 1, 1, 0, 4 plus 2, 6, 1, 1, 1, 1, 0, 16 plus 8 plus 4 plus 2, 30, 1, 1, 1, 1, 1, 16 plus 8 plus 4 plus 2 plus 1, 31. In this method, first the highest number is represented by its representing finger. Further, the rest numbers are arranged by adding the other required fingers. Using this method, the maximum number that can be represented is 31. However, if the same system is followed and the limit of 5 fingers is ignored, then more higher number can also be made. Binary to decimal conversion. Binary number system is based on two numbers, 0 and 1. Therefore, nothing is changed but only number 10 is replaced by 2 and the formula becomes 2 to the power d, where the binary number either 0 or 1 and d is the digit position from right to left. 1, 1, 0, 1, 1 multiplied by 2 base 3, 1 multiplied by 2 base 2, 0 multiplied by 2 base 1, 1 multiplied by 2 base 0, 1 multiplied by 2 base 0 is equal to 1. 0 multiplied by 2 base 1 is equal to 0. 1 multiplied by 2 base 2 is equal to 4. 1 multiplied by 2 base 3 is equal to 8. Now, we can change any binary number into decimal numbers using formula n multiplied by 2 base d. Decimal number system. There are 10 digits 0 to 9 in this number system, and so their base or radix is always 10. Octal number system. As the name suggests, there are only 8 digits 0 to 7 in this number system, and so their base is always 8. Hexadecimal number system. As the name suggests, there are 16 digits in this number system, and so their base is always of 16. The codes of hexadecimal number system equivalent to decimal numbers are given here. Decimal number, hexadecimal: 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, A, 11, B, 12, C, 13, D, 14, E, 15, F. Code 0 to 9 are represented by 0 to 9. 10, 11, 12, 13, 14, and 15 are represented by hexadecimal codes A, B, C, D, E, and F respectively. Conversion system. Now let us try to convert the numbers from one system to another. Decimal to binary conversion. You will now learn the conversion of decimal numbers into binary number. For example, 15 to the base 10 equals to question mark to the base 2. Here, 4 times 1 to the base 2 is the binary equivalent of 15 to the base 10, a decimal number. To convert a decimal number into binary number, you have to divide the number by 2, as the base of binary number system is 2. Quotients are written below the number for the next division by 2, and remainders are written on the right-hand side as depicted in the figure. Remember, remainders are written from bottom to top. Conversion of binary number to decimal number. A binary number, say 4 times 1 to the base 2, is equivalent to 15 to the base 10, can be obtained by using the formula given here. D1 multiplied by 2 to the power n minus 1 plus D2 multiplied by 2 to the power n minus 2 plus Dn multiplied by 2 to the power n minus n, where D1, D2 are binary digits starting from the left side of a binary number, and n is the total length of a binary number. Let us apply this formula on the given number 4 times 1 to the base 2. Conversion of decimal number to octal number. As you have converted a decimal number into binary number by dividing by 2, so to convert a decimal number into octal number, you have to divide by 8. Conversion of octal number into decimal number. The formula D1 multiplied by 8 to the power n minus 1 plus D2 multiplied by 8 to the power n minus 2 till Dn multiplied by 8 to the power n minus n. Conversion of binary number into octal number. To convert a binary into octal, You can make a group of 3 bits starting from right to left. Each group is converted into decimal numbers and finally you get octal number. While making a group of 3 bits, if the leftmost digit or digits is or are less than 3 bits, then you have to put leading 1 or 2 0 before the bit to make a group of 3 bits. Conversion of octal number to binary number. To convert an octal number into binary, first you have to convert the octal into decimal, and then decimal number is converted into binary. Conversion of decimal number to hexadecimal number. In order to convert a decimal number into hexadecimal number, you can divide the decimal number by 16, as the base of hexadecimal number system is 16. When you divide the decimal number by 16, every time you will get quotient, a new number. The division continues until and unless the quotient does not become less than 16. While dividing the number by 16 every time, the remainder is written on the right-hand side of the quotient. Conversion of hexadecimal number into decimal number. 6e to the base 16 equals to question mark to the base 10. The formula d1 multiplied by 16 to the power n minus 1 plus d2 multiplied by 16 to the power n minus 2 till dn multiplied by 16 to the power n minus n is used to convert a hexadecimal number into decimal number. Conversion of binary number into hexadecimal number. To convert a binary number into hexadecimal number, you can make a group of 4 bits starting from the right-hand side of the number. If the leftmost bit has less than 4 bits, then you can put 0 before that group. Each group is treated as itself a digit of binary number system. After converting each binary 4 bits group into decimal, you can write the value from left to right to obtain the decimal number. Binary mathematics. In binary mathematics, you have to manipulate only on 0 and 1. You will learn now to add, subtract, multiply, and divide the binary numbers. You will learn the binary addition, subtraction, multiplication, and division with the help of decimal numbers. Addition of binary numbers. The following rules are applied in binary addition. Formula: 0 plus 0 equals to 0. 0 plus 1 equals to 1. 1 plus 0 equals to 1. 1 plus 1 equals to 10. 0 is written while 1 is remainder. Subtraction of binary numbers. The method of subtraction is similar to addition, although the formula is as following. Formula: 1 minus 1 equals to 0. 1 minus 0 equals to 1. 0 minus 0 equals to 0. 0 minus 1 equals to 1. Borrow from left side. Multiplication of binary numbers. Method of binary multiplication is the same as in the decimal system multiplication. The rules are as given here. 0 multiplied by 0 equals to 0. 0 multiplied by 1 equals to 0. 1 multiplied by 0 equals to 0. 1 multiplied by 1 equals to 0. Division of binary numbers. Binary numbers are divided in the same way as decimal number are divided. Division stops when the remainder is less than the divisor. Boolean algebra. Boolean algebra was developed by George Boole, 1815 to 1864, an English mathematician. In this algebra, the problems are solved by reducing them into a string of yes or no, true or false. Before understanding Boolean algebra, it is necessary to know the basic terms used in it. Let us understand them one by one. Boolean algebra deals with only two quantities, either true or false. The truth value, true, is represented by 1 and the value false is represented by 0. Boolean algebra applies on digital systems which consist of electronic circuits containing switches. That is why it is also known as switching algebra. Let us learn the fundamental operation of Boolean algebra through switching circuits. Logical statements. The statements which can take any of two values, either true or false, are called logical statements. Logical constants. The truth values of logical statements are called logical constants. There are only two logical constants, true, T, and false, F. Binary valued variables. The variables which can take either of two values, 0 or 1, are called binary valued variables. Compound statements. When logical statements are combined with the help of logical operators, they form compound statements. Truth table. Truth table is the tabular representation of all the possible values of logical variables with all the possible outcomes for specified combination of values. Gate. Logic gate is called a gate. It is an electronic circuit which makes logical decisions by controlling flow of electronic pulses. The gate can be formed by an electromagnetic relay, transistors, IC, or microprocessor chip. Logical gates. Logical gates are used to form compound statements. Let us understand these operators one by one. OR, disjunction gate. OR gate is used to perform addition and it is represented by the plus sign. The truth table of OR gate: inputs, outputs, X, Y, Z, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. When X or Y or both are 1, the result Z is 1. The truth table can be written as 0 plus 0 equals to 0. 0 plus 1 equals to 1. 1 plus 0 equals to 1. 1 plus 1 equals to 1. XOR, exclusive OR gate. It is represented by symbol. Here is the truth table for XOR gate. Inputs, outputs, X, Y, Z, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. If either of the inputs, but not both, is 1, the result is 1. The truth table can be written as AND conjunction gate. This gate operates on 2 or more operands. AND operator is used to perform logical multiplication. Dot is used to represent AND gate. Inputs, outputs. X, Y, Z. 0, 0, 0. 0, 1, 0. 1, 0, 0. 1, 1, 1. Only when both the inputs X and Y are 1, the result Z is 1. The truth table can be written as 0.0 is equal to 0. 0.1 is equal to 0. 1.0 is equal to 0. 1.1 is equal to 1. NOT negation gate. This is unary gate because it operates on a single variable. It is also called complements. The tilde or comma symbol is used for NOT gate. Here is the truth table for NOT gate. Inputs, outputs. X, Z. 0, 1. 1, 0. NOT gate inverts the inputs. If the input will be 0, then output will be 1. But if input is 1, then output will be 0. The truth table for NOT gate is as 0 bar is equal to 1. 1 bar is equal to 0. If the value of X will be 0, then the value of Z will be 1. But if the value of X will be 1, then the value of Z will be 0. So, you can find the equation Z bar is equal to X, where the bar inverts the value of Z. NOR gate. NOR gate is an inverted OR gate, that is, an OR gate followed by a NOT gate. The following truth table illustrates the result of NOR gate. Inputs, outputs. X, Y, Z. 0, 0, 1. 0, 1, 0. 1, 0, 0. 1, 1, 0. When the value of X and Y are 0, the output is 1. In the first step, OR gate takes action and the output becomes 0. In the second step, NOR gate takes action and 0 is inverted, so it becomes 1. The same action is performed on remaining inputs. NAND gate. A NAND gate is an inverted AND gate, that is, an AND gate followed by a NOT gate. The following truth table illustrates the NAND gate. Inputs, outputs. X, Y, Z. 0, 0, 1. 0, 1, 1. 1, 0, 1. 1, 1, 0. The logical gates OR, AND, and NOT can be used to perform mathematical operations. These functions are performed by Arithmetic and Logic Unit, ALU, a part of CPU. Switch. A switch is an essential device that controls the flow of current in circuit. An open switch. When a switch is off, no current flows in the circuit. The off state of a switch is called an open switch and represented by binary code 0. A closed switch. When a switch is on, current flows in the circuit. The on state of a switch is called closed switch and is represented by binary code 1. Switching circuits. Let us understand NOT, and OR through switching circuits. OR gate. Let a switching circuit contain two switches, A and B, and one lamp, C. Let switches be connected in parallel. Switching circuit for OR gate. In the circuit, the bulb will glow if any one of the switches is closed. Following is the truth table that represents the relationship between switches and bulb for OR gate. A, B, C. 0, 0, 0. 0, 1, 1. 1, 0, 1. 1, 1, 1. AND gate. The AND gate can be represented through two switches, A and B, and a lamp C. In this case, the switches will be connected in series. Switching circuit for AND gate. Following is the truth table that represents the relationship between bulb and switches for AND gate A, B, C. 0, 0, 0. 0, 1, 0. 1, 0, 0. 1, 1, 1. NOT gate. NOT is an unary gate and it operates only on one switch. Let a switching circuit contain a switch A and a lamp C. Switching circuit for NOT gate. If switch is open, then the lamp will glow, and if the switch is closed, the lamp will not glow. The following truth table represents the relation between lamp and switch A, C. 0, 1. 1, 0.